Hi everyone, and this is a new video tutorial about tensile test simulation using Abaqus. In this video we will learn some basic of failure analysis using element deletion. We will use the plasticity property and elastoplastic property, failure property, and use also element deletion. I hope to enjoy with this video. Let's get started. First, let's start with creating our specimen. Creating part. Let's get the name of the part. Tensile test specimen. 3D deformable solid revolution. This time we need to use revolution option. Continue. Sketch our part for revolution option. First line, second line, third, no, we have problem in this error. Let's add some quotation. First, no, select first point, second point, and give it a length of this line 90 millimeter. The second line is 5 millimeter. Enter. 40 millimeter. 30 millimeter, and we have 10 millimeter in this line. Let's create curvature in this corner. Use this option, create arc tangent to adjacent curve. Select the first point. No. Click first point, second point. We have curvature. And now we need to convert this line to construction line with this option. Set as construction line on this option, converting line as construction line. Click the line, done, and click done. Now Now we have construction line to make a mirror option for this sketch. Select the type of mirror operation. We need to copy the wall sketch. Copy and pick the mirror line. Select the bottom line. Click done. Select the entities to mirror. We need to mirror all this line. Click done. Now click done, and now select the construction line to act as the center line. We need this line as construction. You have this line, and now we need to enter the angle of rotation of or revolution. We have 360 millimeter, 360 millimeter. Click OK. Now we have our specimen for tensile test. Now we need to create partition of this specimen to simplify our model. Now create plans to create partition. We need to use option to create partition using 3 points. We have many options to create partition. Let's select first one. Partition cell defining cutting plan. Partition cell use datum plan. Partition cell extended face. Partition cell sweep. Partition cell and use inside patch, and many others option. Let's try with it. Select edge. No, I think we have wrong. face plan. Select corner point. Let's try with now with this wrong option to create partition. Now we don't have any datum plan. Let's use this. Let's use this option to point and normal, or 3 points, or normal and edge. Let's use 3 points, but this is wrong option also, because we don't have 3 points in this plan. Let's try another option, points and normal. Select a point, this point and this normal, create partition. Now we have the first part, first cell, the second cell. Now select Tensile for creating partition. Click on point and normal, select point, select normal and create partition. We have 1, 2, 3. Now we need to create partition in this cell. Done. Point and normal, point, normal, create partition. Select cell. Done. Point and normal, point, normal and create partition. Now we have a great partition of our model. Let's add another partition of the wall model. Select all cells. We need to use 3 points. First one, second one and third one, and create partition. Now we make partition of the wall part. After finishing this creating of our part, let's go to property module and create our material and add property. Create material. Let's give it a name, steel material. Steel. We need to add general density. We need to use the density because we need to make dynamic analysis of our model. In this model we work with Newton in the force, and millimeter in the dimension, and megapascal in the constraint. And in the mass, in the density, we need to use the ton to millimeter cube. This means we have 7.8 E minus 9 ton per millimeter cube. We don't need to use this in there, but this for explication. The density is in the ton to millimeter cube. 7.8 E minus 9. Now we need to add elastic property of our steel, megapascal, and pushing ratio 0.3. Click OK. Now we need to edit this material. Edit. Now we need to add mechanical plastic property of our steel material. Now we have this parameter. Now we have all property of elastic property. This is our elastic property, plastic property. I'm sorry. Now we need to add some damage for ductile metals. ductile damage, we need to add fracture, strain, stress, triaxial, and strain rate. First 0.25 and 1.35 and 1, and we need to add zip option for damage evaluation or damage evolution. We need to add displacement at failure that equal to 0.65. click OK, and OK. I think this is all material property we needed in this simulation. Click OK. Now we are creating the material. The second step, we need to create section, steel section. Solid, homogeneous, continue, and select the steel material. Now we need to add this material and their section to this specimen. Click assign section icon, select our part and select steel section. Click OK. Now we have material assigned to our specimen. Click done. Now we need to go to assembly module, click create instance, tensile test, apply. Now we have this specimen in our assembly. Go to analysis, step module, create a new step, dynamic step, create dynamic explicit, click continue. Now we have nonlinear geometry is checked on for this property because we have elastoplastic material model, increment, basic, we have time period, incrementation, and mass scaling. This option is very important to make our process and computing time and to minimizing our computing time. Let's use this option. Use scaling definition below, create one. We need to add this option. Let's add 100 and 5 power minus 6. This option for simplifying and minimizing the computing time. This option is only used for dynamic analysis. Click OK. We have this parameter 100 and click OK. Now we need to go, or I think we should to create 2 reference points to simplify our model and make our model more sophisticated and simple to manipulate. Create the first reference point, select this top option, first reference point, and the second reference point. Now go to the interaction module. In this module we need to create interaction between we need to create 2 interactions. The first one between these 2 cells in the top with this reference point, and in the bottom we need to create coupling interaction between these 2 cells with the second reference point. Let's start with the first reference point. Create constraint, first one constraint 1, coupling, continue. Let's select constraint control point, the first one, click on it, click done, and select node region and select these top cells of our model. Click done. We have our coupling parameters, kinematic and constrained in all directions. That means this point is the leader of this all zone. This point is this part, these two cells we selected, is depending to this reference point. Click OK. This is the first coupling interaction we have. Let's create the second one. Create constraint to coupling, continue, select the second reference point, yes, node region, and now we need to select these two cells in the bottom. Click done. Now we have 2 points, 2 coupling and 2 interaction in these two zones. Now we need to go the load module, and we need to create boundary condition of our model. First we need to create encaster in the bottom surface, in the bottom part, or in this zone that represent the clamping zone, the first one and the second one. This is the fixed clamping zone, and this the moved clamping zone. Now we need to create symmetry, axis symmetry encaster. Click continue, and we need to select the reference point that represent all these two cells in the bottom. Click done and create encaster. OK. Now we add the boundary condition of this top part, top cells. Create displacement rotation, continue, select the top reference point. We have a free movement in this direction, y direction. In this direction we have free movement to allow the clamping to move in the y direction. We have this free movement. Click OK. Now we have two boundary conditions. Let's move it to the left. First one, second one. The third boundary condition we need to add is the displacement in the y direction. Create one boundary condition. Let's name it displacement. Continue, select the top reference point, RP1, click done. We have displacement in this direction. Let's make it 25 millimeter. Click OK. Now we have an error message. In an explicit analysis step, an amplitude must be referenced if no zero displacement are specified. Now we need to create amplitude load, or amplitude to in our load. Now we need to now we have our amplitude of our load. Must contain empty cells. We have an empty cells, I think. Now we have one in these cells. Click OK. Now we have amplitude. Let's select the amplitude we are creating. Click OK. Now I think all things is done with this module. Let's go to mesh module and create seed. Let's make dependent part, dismiss part, seed part or size of element. Let's make it 5 millimeter. Apply. OK. Let's make it hexagon, medial axis. OK. Let's meshing the part. Now I think need to add more size, add more refinement of our mesh. Click 2, delete the previous mesh, click OK, apply, OK. Now I think we have a great mesh. Now we need to go in these assign element type. Select the part, click done. Now we need to use explicit library element, and we need to add the option of element deletion. Let's make it yes, element deletion. Select yes. Maximum degradation, let's specify the value 0.95 and click OK. For getting and extracting the result of force displacement, we need to go to step module and we need to create a reference point when we need to get the force displacement curve. Let's create this reference point, this set point. Set tool, set create reference point or reaction force, geometry, click OK and select the top reference point. Click done. We have the set now. This set. Now we go to history output manager and click on it, create a new one, history output 2, continue, and now we need to select this set we created, reference reaction force, and select the displacement and the reaction force in this point in the y direction. Let's go displacement in the y direction u2, and reaction force rf2. We have these two value, these two quantity. Click OK, dismiss. Now I think all things are done. Go to create our job, create job 1, continue. We have many options there. Click OK and go to data check. Let's check our module. Now we have successful check of our model. Let's continue our process and simulation. Continue, click OK, submitted. Running, and it takes time. Now we have completed job. Let's go the result and show our result. We have our specimen, we have deformed shape. Now we can see the failure of our specimen in this zone. Let's make a movie and animate this simulation. We have the failure, this is our result of our test simulation of tensile test. Now we need to get the force displacement curve. We need to go to ODB history output, continue, select the reaction force and special displacement. Now we have these two reference value. We need to plot the result in it. We need to plot and get data of reaction force and displacement in the top of reference point, in the top reference point. Now we click plot. We have this curve, these two curves with force and displacement. Now let's save it as is. Click OK, and we should to create the force displacement curve. Go to operate on XY data, click continue. Now we select combine in the operator side, select combine, click on it, and select displacement. We have the displacement and reaction force. Now plot the result. Now we have the curve of force displacement. We have this curve of force displacement of our simulation test of tensile. Now let's go there and let's click on activate and deactivate linked viewports. Click on it. We have this result. We have the force displacement curve. Now we need to go to this viewport, and now we need to get the strain stress curve. Go to this create XY data, ODB file output, click continue, and we need to get some parameters. We need to get logarithmic strain component, plastic strain component, and equivalent plastic strain. We have select the second stress, the stress in the second direction, in the y direction, S to 2, and now we select one of these parameters, plastic strain. Let's plot. Now we have an error. At least one entity should be selected. Let's select the entity. Click on it. Let's stop the animation and go in the first step. Now click on edit selection and select one of element in the middle of the specimen. Click plot. Now we have these two curves, the strain and stress. Now I think we need to do the same steps for the force displacement curve. Let's save as is. Click OK, dismiss. Now we need to go to operate on XY data, click on it, combine, but we have these. I think we have a problem in this data. Let's go from the start, delete all of this data for avoiding any collapse between data. Delete all this data, click on it, click OK. Let's do this from the first. Click create XY data, ODB file output, continue. This value, element selection, edit selection, and select element in the middle, plot the result. We have the result, and save as is. Click OK. Now go to operate on XY data, continue, and combine. Strain, stress, plot the result and the curve, and we have the strain stress curve. Now we have this result of strain stress curve. Strain stress. Finally, I hope to enjoy with this video, and I think we have many idea and many better things we can find in this video. Don't forget to subscribe and make like for this video. See you soon.